Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome back in lecture 5. Students, as we start equivalent prime method, we start an example, okay, which was this example. And in lecture number 3, basically we covered this example up to this point. In lecture number 4, we basically covered this whole portion, okay, and lecture number 4 ends at this point. Clear? Now after this, what we need further, we have to run moment distribution table. But before going towards a moment distribution table, we need some other relevant material which we need to run that distribution table. For that, what we need basically loads. Okay, so for bending analysis, basically we need as we have the slab load, okay, ignoring the other finishing loads, etc. Okay, if those loads are exist, you have to find it and find out total dead load. Then live loads, okay, and you have to multiply that loads because that are the loads which act per square feet. Okay, so for square feet you have to multiply that load with the width of the beam, slab. Remember, we are basically dealing with slab beam which covered both slab and beam. We are not did the analysis just only for slab or just only for beam. So that's why we have to convert the load to kip per feet. Clear? But for shear analysis, yeah, this is very important, as in case of shear analysis, we have to find out the beam reb load, and we have to use the tributary area concept, because although we can use this load as well, but it is a little bit uneconomical procedure. We need to find out the tributary area, because in that case, in shear case, we are just purely analysis, we run analysis for beam, not for slab. Okay, so that's why basically that the load for shear, it is different from load for slab beam. Clear? Now the tributary area is this one. As let me explain this concept. You see, this is the tributary area as you see here, okay, and this is the tributary area for this span, and this span. And I think you all will be familiar with the tributary area. We have to find out the half portion, that is the total span length divided by 2, and similar to that set, the span length divided by 2. As here we have a similarity in geometry. This means all panels are 20 feet in this direction and 25 in this direction. So we just pick one of them, okay. We just showed here, we show the tributary, the trapezoidal loading, and then we convert that loading. This is the tributary area. And next, finding this area. Once you find this area, that is 150 square feet roundabout, clear? Now you have to just multiply your load, that is you find out per square feet. With this you got the load, total load, and if you divide this by 25, you got load per feet. Clear? This is important. Now you see here, we find out the tributary area, we multiply that with the per square feet load, not with 1.75. okay, we have to multiply this one and divide it by the length to convert it to kip per feet. Clear? Similarly for we have multiplied by 2 because we have other side. You see here in this picture, we have this trapezoidal and this trapezoid, so that why you have to multiply it by 2, and we find this one. Similarly, including the reb load. So here you see in this picture, okay, we have to add this reb load. How to determine the reb load? This width times this depth times the density of concrete. And sometime people may take this load, this black dashes you see here, although in this case we are not taking, because if you are taking the centroidal distance, center distance, sorry, as in this case 10 feet, okay, in 10 feet, because we are using the center to center distance, not the clear spans. So that's why we are ignoring this portion. Okay. So we include the rib load, and in this case the dead load will be this one and the live load will be this one. Remember, these loading will be used for shear analysis in later stages, but these loading will be used for or bending analysis, for bending moment calculation in case of slab beam. Okay. So further we already do these calculations in lecture number 4, and what we need basically, we need distribution factor, because we have to run distribution moment distribution table. So for that we need distribution factor. So how to find a distribution factor? I think you already know this. For this AB span, K is B of this span divided by K is B of this span. Okay, so but remember, at this joint we have this beam and we have this column. So that's why you see 349, that is the K is B of this beam plus KEC of this column. Clear? So for AB, our distribution factor will be this one. But for this column, you see here this column, the distribution factor will be KEC of this column divided by the stiffness of this column plus stiffness of this one, this beam. You see here. Similarly, AB, for AB, as it's a joint having two beams and one column. So that's why you see the calculation here. So for distribution factor for BA span, it will be this one. For this C1 column, the distribution factor will be this one, and BC, distribution factor for BC, it will be changed. Okay, that will be the KSB of this one divided by KSB of this one plus KSB of this one divided by KSB of this one. So now you see for BA this one, BC you see this one. Clear? That will be same as for BA. And for the rest of the span it will also be same. If the lengths are, the distribution factors, sorry, the stiffnesses are different, then you have to calculate for rest of the spans. Clear? Now we have to find out effects in movement, because we need it. We already determine, okay, we already know this formula, but is already in the beginning of the lecture number 4, I already show you that we don't, here we will use this one, we have to use this one, and this is from table A14. Okay, we already determined this value in lecture number 4. Now we just show the, we first of all we do the calculation for top story. Here we have for top story, sorry, this is the calculation for top story, the distribution factor for top story. Clear? And for the top story only, you see these values will be is different. Okay, these values is only different, the rest of the calculation is same. Clear? And you see all the panels. Okay, for AB the distribution factor will be this one, for BA the distribution factor will be this one, and for this column this one will be used, and for this H column this one will be used. Okay, and you see the rest of the calculation. I think this is not difficult process if you are familiar with the moment distribution method. Now this is the table which I draw here. You see joints, you see carryover factor, we already determined this from table F14. Okay, in lecture number 4, you see at the joint of AB we will use this carryover factor. At BC, although in our undergrad courses we use more carryover factors half, 0.5, but here you see that this one will be different. Similarly this one at BC for CD, although the spans are same, that's why carryover factor is same. If the spans are different with a different geometry, then these carryover factor will be different. Clear? Now members, we have this is a little bit, you can say, cantilever portion. Remember, let me draw here. Okay, you see sometime you see this is each column, this is slab. sometime a portion of the slab is cantilever to this side, sometime. So if there is any cantilever, I will do some one of the example, in that you will see this cantilever portion. So sometime a slab is cantilever. So for if there is any cantilever, so we will show that cantilever portion here by slab. But in this case, I am considering it as equals to 0, similarly to this side and this side. Now C2 column, that is the edge column, then AB span, then BA span. Remember, this is for interior story. This table which I draw here is for interior story and only for dead load analysis. Remember, only for dead load. This is very important, not for live load. Okay, not for live load. This is for dead load. Why for dead load? I will explain the reason. Okay. Now we have C2 column, then span AB, then span BA, C1 column, which is the interior column, then BC, CB, and similarly again the things are repeated. Then we have distribution factor. We already determined the distribution factor. Okay, I assign this equals to 0. Similarly, I determined for C2 and AB, BA. Okay. Then fixed end moment. Okay, we already determined it. That is for AB span, that is 0.084 times WU, that is 1.75 WU. Okay, here for dead load. So dead load is how much? Dead load is 1.74, 75, I think so, kip per feet. So L square, you just plug the value, you got the answer. Okay, I think so. Here I did it in this 0.084. Okay, WU L square. Clear? And balancing now, this is important. What we done here, we have to multiply this, we have to sum these values, these three values, and multiply these values with these distribution factor. So we got, from the addition of these three values, you got 91.88, multiply with this distribution factor, you got this one. But you have to change the sign. Clear? You have to change the sign. And then you have to multiply this movement with this distribution factor, change the sign, you got this one. Similarly, here at this joint B, you have to add these values. Clear? You have to add these three values. Okay, these movements, which is the fixed end movement. As you see here, remember, this is very important, that here I am considering, let me show you here. Here I am considering this movement as negative. Basically, this anti-clockwise movement will be represented by positive sign, and this anti-clockwise movement, clockwise movement will be represented by a negative sign. Clear? This is very important to understand right here, because you see here BA span is having a positive negative, I have a negative movement. For example, let's say this is A and this is B. Clear? This is B. So AB have, you see here, we denoted it with a positive sign, and similarly here you see we denoted this moment with a negative sign. Similarly at BC, okay, BC, the moment which is right here will be denoted by a positive sign, and the moment at C will be denoted by with a positive sign. Clear? So here you see this is with positive and this is with negative. And similarly CD, you see CD is denoted by positive while DC moment is denoted by negative. Now balance you already know, and carryover factor is basically half. Remember the carryover factor. This table is a little bit tricky. Okay, from A to B movement, okay, half movement will go toward this side. From B to A, half movement. Clear? Similarly here you have to just look to these two tables. Okay, here and here. Clear? Similarly here. there will be a carryover, clear? And similarly here, clear? This must be remembered. Now after calculation is, let me show you here. We already calculated this loads and we just show the loads. Now after showing the loads, calculation of distribution, and this is the final moment distribution table, I try my best to draw this table to basically in Excel by myself. So let me share that table and what are the results to come, and we will compare these results with that Excel sheet. So this is the sheet, okay, which I created for this question, for this moment distribution table, but this is for top story. Let me show it for intermediate story. This is for interior story side. Now for interior story, you see here this slash line, this is for interior story. The table is same as I discussed earlier, and the fixed end movement you see here, 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 this one, okay. Now you see the balancing, okay, which is coming from the combine and multiply with that one. Similarly this one you see here, although it can be extended, okay, let me extend it, okay. And similarly you see this one, okay, similarly you see this one, okay, because you see there is negative and there is positive, so they cancel each one and multiply with this one, so this comes out to 0, so that when 0 multiplied by that term you got 0. But only things, okay, here you see this one and similar this one. So this is the way that how you can create this table by yourself, okay, for your own study, okay. Similarly balancing, you see here, no carryover, you see half coming to this side, similarly half coming to this side, but remember it is not just half, it is only this one, okay, carryover, clear? So this movement is divided by this factor, and similarly here this movement is divided by this one, and similarly by this one. Although in our bachelor basically we half movement coming toward this side and half movement coming toward this side, but here carryover factor is different. And once you complete this table, just copy these two cells, clear? Copy this and paste right here, okay, paste right here, and this is similarly follow the procedure up to when you got, okay, 0 0, clear? So after this I just use the sum formula and I got these values, okay, you see here, okay. Now let me compare, okay, you see here for an interior story minus 44, 44, and all these movements are similar to this one which I have calculated right here, clear? Now similarly for top story, okay, I draw the same movement distribution table, I assign the same load, remember I applied the same load, so the load is same, only the difference is the moment distribution tab or distribution factor, okay. The rest of the things are same for interior story and for interior story and for top story, okay. Now these movements which we got here, now these are the support movements, remember these are the fixed end movements, we can say, at the supports, okay, at the supports. Now what we have to do, we have to find out the positive movements, okay, at the mid span movements. Now as you see in this lecture, they basically draw this table for interior story and then for top story. Now you see here this table, okay, this diagram, this 2D diagram, this is very important to understand. You see from where these movement they bring, okay, this is very important question. Clear, right? You see here, you see the span A, B, C, D, E, okay. Now these movement is basically from that movement distribution table. Okay? From, let's say for interior story, you see minus 44.66, so you see 45 roundabout, this is 109, so you see 108, because you see, you must understand from where you have to pack the moment. This is span AB, so AB, BA, BA, you have to search here BA, and this is my BA, so that's why I'm taking this moment. This is with a negative sign, and this is with a positive sign. Positive sign means that this movement is in anti-clockwise direction. Negative sign means this movement is in clockwise direction. Similarly, for BC, you have to choose this one. For CB, you have to choose this one, and so on. Clear? So once you got these movements and you represent these movements, what we have to do, we have to find this positive maximum bending moment. Okay, similarly this one, similarly this one, and similarly this one. Okay, so this is our, okay, now our next task, to find out these moments. Yeah, to find out these moments. Now to how to find these moments, we have to use the techniques which I will explain in my next. Okay, so I just show those movements right here. You see which movement is positive and which movement is negative. So this movement is negative, this movement is negative, this one is positive, this one is, sorry, this one is negative, this one positive, this one positive, this one negative, and so on. Clear? I think so. This movement will be 109 and this one 11. Clear? So this is for interior story and this one is for top story. For top story, you have to come here, and from there you will choose these two movements. Okay, these two movements. Clear? And similarly these two, these two, these two. Clear? So after this we have to do some other calculations as we did in our bachelor's. Okay, what we have to find out, we have to find out the positive movement right at this midpoint and this midpoint. Clear? As I show here. So I did this whole calculations. You see this 64, this 67, this 44. From where these movements come, let me discuss it. Okay, so where is the rest of the notes are? The rest of the notes are now let me edit it. Clear? You see these black sign up interrogation sign. Okay, we need to find out these movements. To find out these movements, the next procedure is that we have to use the technique which we already, I think so you all will be familiar with this. Okay, what we have to do, this is for interior story. Remember, this is for interior story. Clear? This is very important. This is for interior story. Now the dead load is assigned. Clear? These are the same movements which we already calculated for the interior story, and what we have, these reactions are you see these reactions is due to these movements, these support movements. You see this movement is maximum as compared to this one, so this span AB will tend to rotate in the clockwise direction. Okay, so to bring this AB span or AB beam in equilibrium, we have to apply an anti-clockwise moment. So therefore the reactions you see here, this reaction will be in downward direction while this reaction will be in upward direction. So this reactions will produce an anti-clockwise movement which will balance that net clockwise unbalanced movement. So this is 2.5 and this is 2.5. Okay, you see here how we got 2.5. This plus 45 minus 109 divided by the span length of this beam AB, you got this minus 2.5. Okay, minus 2.5 means we have to apply an anti-clockwise reactions. Okay, similarly here you see this 21.88 and similarly 21.88. Basically these reactions are due to external loading. External loading means we have applied 1.75, so 1.75 multiply by 25 divided by 2, you got 21, and these reactions will be in upward direction. Clear? So the net reaction will be at this point, you see 19.31. Clear? Okay, you see this is in upward direction, this is in downward direction, so subtract these two, you got this one. But here the case is a little bit tricky. You see here that you see here at this point that here we have 0.55 which we obtained from these two moments, 101 plus 101 minus 87 divided by this span length 25, you got the 0.55. and here you see this BC beam section is in, you can see it will rotates in an anti-clockwise direction, so we have to apply a clockwise moment. So that's why this movement is in upward direction and this one is in downward direction. Clear? And similarly here the same UDL loading, and due to that we have to apply an external reaction. So at this point we have 4 reactions basically, and all the 4 reactions in upward direction. So that's why we have to add up this one, clear, similarly this one and this one, and what we got from this 46.86. okay, similarly do the same calculation for the rest of the spans, and similarly here you see 42.66. these 2 reactions are in downward direction and these 2 reactions in upward direction, so add these 2, subtract from the summation of these 2. Clear? And do the rest of the calculation. Now we have to draw shear force diagram. Okay, so here you see the shear force diagram. This is 19.31 kip will go in upward direction. Then we have a UDL loading. You see here this UDL loading, it will bring down this shear to a negative point. You see here 19.31 minus 1.75 times 25. okay, so this will be a negative shear, and then we have a reaction that is 46. So 46 is a positive reaction, so it will try to up, okay, this point to this point 22.42. you see the calculation. Okay, similarly again we have a UDL loading that tends to bring this point again here, and you have to subtract that UDL. okay, now the shear will be at this point. okay, you have this one. Similarly again we have this reaction, it will picking up this point to here, and you see then again you have UDL and it will bring down here, and you see the rest of the calculation. Now remember here we must get 0. If we don't get 0, So this means, it means the shear which is calculated at this point should be equals to this one but opposite hand sign. Then you will get 0. If you don't get 0 value, this means that your shear calculation is wrong. You have to repeat your calculation. Now the next procedure is that we have to find out, we have to draw a bending moment diagram. So this shear diagram basically helps us to find out the bending moment. Clear? So 45, we already know this moment. Where this moment is, you see this 45, which is in anti-clockwise direction, a negative moment. So here we see this 45. Now we need the maximum positive moment. So how we get this moment? We have to this a negative, and you see the shear area. So this shaded area we have to find out. How to find out? We have to find, remember, the point where the shear is 0. So for that, what we have to use, we have to use the similar triangular rule, okay, over these two triangles. Clear? Similar triangular rules. This means 19.31 divided by x will be equals to this minus r 24.44 divided by 25 minus x. Okay, and I show you this calculation. I doesn't show you this calculation, but it will be easy. Okay, so you people can do this. Clear? And okay, let me show you what we have to do. Okay, so 19.31 divided by x will be equals to 24.41 divided by 25 minus x. So simplify this equation. You got the value of x, that is 11.03 feet. Or you can easily do this calculation by just subtracting the UDL. Okay, as we see, the reaction at this point, the shear at this point is 0. So if we write down the shear equation at this point, which will be looks like in this shape, the 19.31 minus, as we have a UDL loading right over here, so that's why we have to subtract that UDL from this one, that is 1.75, as this distance is x, so multiply with x, and the shear, the net shear will be at this point will be equals to 0. So simplify this. For x you got 19.31 divided by this. Okay, so this is a simple procedure. Okay, you got 11.03. Okay. So this is the procedure that I got 11.03. Now you have to find out this shear area, subtract or add. Okay, this is a negative, so add it, because this is positive shear and this is negative moment. So you see the calculation. Okay, how I got 64. Clear? 64 minus 45 plus 19.31 times x, because this is moment and this reaction. So let me draw here. Okay, let us see this calculation. Okay, we have a moment right here, 45. Clear? And similar, this is my section. Let's say my section is this point, so the distance is x. Okay, and we have a UDL loading, that is 1.75. Okay, so what will be the value of movement right here? Whether it will be a positive, so it will be a positive movement, and what will be the value of that movement? Clear? So the movement value will be 45. Let's say this movement is negative. Okay, here we have this reaction, and this reaction is basically 19.31. Okay, so that reaction, you see, this basically tends to a positive moment. Okay, So 19.31 times x, and again negative sign because this UDL causing a negative moment. So 1.75 times x, as it is a movement, so that we have to multiply half of this distance. Okay, half of this distance, that is x divided by 2. So it will generate this equation. You see here, you have to just plug the value of x, that is 11.03, you got 64. Similarly here, okay, 64. Now let me show you this value 64. Okay. So this is the way, okay, this is the way how you got these values 64, 43, 43. Although there will be a little bit difference, but you see 64. Now the same, okay, this is 64. Now from this 64 you have to just subtract this negative shear area, you got 109. Okay, but already we know this 109 moment. This 101 is already known to us, so we have to find out this 43. So 101, you see this is negative moment, plus you see this shear area. Basically they add this shear area. Although remember, you can find this 64 by just adding this shear area, or either you can write down this equation. So there are two ways to calculate this 64. Similarly, you see here, they're just simply adding this positive area, okay, half times 22.42 times 10.8, 12.81. Now again they calculate this x. Okay, you have to calculate this x, you have to calculate this distance, you have to calculate this distance. Okay, so then you add up this shear area, you got this 43. Again repeat the procedure, as at this point we already know the moment. Clear? You see here we know moments 87, so 87 plus this area, you got what? You got this 43. Similarly for the rest of the points. So this is the way which I want to show you the whole calculation, how they got 64, 43, 43 and this value. Clear? And already we know these values from moment distribution table, E45, 109. Now you have to repeat the same procedure for top story, and you have to find out this 67, this 42. Clear? This is a very lengthy calculation, that's why the whole calculation which I share with you people, okay, this whole calculation I try myself to make this easy, and I draw this whole calculation, I summarize this whole calculation in my Excel sheet. So you see here the moment distribution diagram, the shear force diagram and the bending moment diagram. Clear? And you see we have those spans A, B, C, D, E, and we have those movements. Now these movements are okay, these movements are basically linked with this sheet. Okay, so these movements are basically from the moment distribution table. Clear? And similarly these are the spans. Okay, these are the reactions which I already shared. These reactions and these reactions I already shared with you people, and these are the net reactions. Okay, these are the net reactions. Now after that, these are the shear force values. Okay, these are the shear force values, and these are the maximum point. Okay, these are the distances that at the point where shear becomes 0. But remember, as the point at which shear becomes 0, we already know there will be a maximum moment. So you see, this is the maximum moment point. So this is the maximum moment point, that is 11.03, and you see how I did it. Okay, this reaction divided by the this 1.75, because I already shared this. Okay, here you see here that is x can be calculated by just dividing that force divided by this UTL loading. Okay. So you see whole calculation, this 43 here I got basically 42, although this is 64. This is a little bit difference because due to rounding up errors and somewhat like that. Okay, but this is close to 64. Clear? And these are the lengths I already calculated, because this A point is a distance 0. After that, at the maximum moment, which is right here, it lies a distance of 11.03. Then we have a B point. At B point we have this side 25 and that side 25, and so on. Clear? So this is the whole calculation for interior story. Okay, this is the moment distribution table and these are the net moment. Similarly here, these are the calculation for a top story, and this is the calculation for the top story, which I have already calculated. 67, you already see this is the maximum moment. Okay, this is the maximum moment, this 42, this 42. So let me, you see 67, 42, 42, 67. So I share the calculation basically for only one interior story, and for the top story I did the same calculation in my Excel sheet, so it will help me. Okay, and it makes the calculation easy because I have to again draw these diagrams, and this is a very lengthy procedure. So that's why I draw the same calculation. Okay, and you see the results. Clear? So for top story you see, okay, the whole work, that how I got these 67, 42, 42 and 67. Okay, so in next lecture inshallah I will share, because this is a tricky part. Clear? And there are some other difficulties as well, because you people will see how we will use graph S7. Clear? So that inshallah I will cover this in my next lecture. But before finishing this lecture, I would recommend you to go to my YouTube channel, and I already uploaded a DTM method. Okay, DTM method, and the application of the DTM method in case of such slab supported system, in the beam slab supported system, which the example which we will cover in this lecture series. So if you watch those lectures which I uploaded relevant to a DTM method, but basically we see that DTM method is helpful for the analysis of flat slab or flat plate slab system. But when we applying the DTM method to a such slab system having beams, okay, so the DTM method would be a little bit tricky, lengthy calculations and a complicated procedure. In that case we applied basically equivalent prime method. Now I already uploaded lectures that how to apply a DTM method when you have a beam slab supported system. Okay, because in YouTube you don't find such videos, okay, which covered a DTM method to a beam slab supported system. So you must watch those lectures before lecture 6, which will be a next lecture. Okay, because I will use this graph F4, and I will use some other concepts which I'm not going to explain. Okay, because we have to use, you see, alpha factor, what is beta factor, okay, and there are other some factors. Okay, so you must have an idea. Okay, from DTM method I already uploaded 15 to 14 lectures. Okay, from the beginning, from the first 2 lectures are relevant to this alpha beta factors, and similarly the application of a DDM method to a beam slab supported system. So then you will understand this table very easily. Thank you for watching. See you in next lecture.